So you have just experienced a volumetric pipette laboratory experiment. I know it wasn't very hard. At least the intention of it wasn't a very hard lab. The thing, though, is that this is a technique course. So instead of really looking at results all the time, we are focused on your technique. How can we improve the way that you behave in a laboratory to ensure that you are using these tools correctly? And what you found in the volumetric pipette lab is maybe this concept that volumetric pipettes are not hard to use, but they're tricky to use the proper, and that's the key word, proper way. So we are going to follow up this volumetric pipette lab with something that's called a micropipette. Now, a lot of people really enjoy this idea of micropipette because I'm going to get ready to tell you that micropipettors are a way that we can automate the volume deliveries. So no longer do we have to go to glass volumetric pipettes and use those with a bulb and suck up solution to the line of the volumetric pipette. The micropipetter will simply be dialed into the proper volume, and that volume will be sucked up into a tip, and then you dispense that volume down into a container, and it is very automated. The problem here, though, is that it's technique. Can you use the micropipetter the proper way? So what you see on the screen right now is a micropipetter. Now, there's two different versions that you're seeing on the screen. One, here to the left, is called a single channel. Guess why they call it a single channel? That's right, because there's only one little stem at the bottom, and that's it. Over here to the right-hand side, this is a multi-channel pipetter. So this is typically used in the biology world, the biotechnology world. Anytime that you are processing a lot of samples the same way, for instance, a 96 well plate. Could you imagine pipetting the same thing 96 times and then turning around and going back to another solution and pipetting that one 96 separate times? No, this is crazy. Why do we want people to go through that torture? So a multi-channel micropipetter will do that for us much easier and much quicker than a single channel would be. Now, what you're going to be using most of the time in our lab facility is going to be a single channel micropipetter. And again, the intention here is to make the volume delivery much easier. So go back and think about what you did with the glass pipettes. We had you to deliver two volumes, a 1 milliliter and a 0.7 milliliter. Now, some of you got lucky. You did 1 mil, 1 mil, 1 mil, 1 mil, 1 mil, and you provided the numbers, and we said, good, pass, go on to the next one. Others, though, you were pipetting, and when you pipetted, your numbers were maybe off, which means that you weren't really pipetting the proper way. So the 1 mil and the 0.7 mil are typically the trickiest because these were the smaller volumes that happened during that lab experiment. No one wants to go through the headache of doing these really small volumes. Hence, the micropipetter was born. So it is an automated tool, very nice when we say the word automated, and it's supposed to make the process easier for you. Oh, well, now this is music to my ears. It's automated and it's easier? Well, why not use this thing, right? But the problem is that our micropipettors do not pipette large volumes. We just don't use them for that purpose. So that's why glass volumetric pipettes are still in the lab, and we still use them, and we use them all the time. It's the smaller volumes that typically cause us problems. So, for instance, in a lab, it's not uncommon to pipette 0.1 milliliter. Could you imagine? 0.1 mil? I mean, we had you to pipette 0.7 mil. What about 0.1? Okay, well, that's not the smallest we can go. What about 0.01 mil? Yes, we can do that in a lab. We can go to super, super tiny volume amounts. and a micropipetter is going to be used for that purpose. So the normal size here for a micropipetter is a 100 microliter to 1,000 microliter solution or volume. And then we have another size in the lab that typically floats around, and that's the next size down, and this will go from 10 to 100. So pretend like you're buying baby clothes. Okay, the 10 to 100 is one age bracket, and then the 100 to 1,000 is another age bracket. In micropipette land, folks, this is regarded as a large volume and a medium volume, but we can go even smaller if we need to. We just don't typically do that in our lab for our purposes and what we need. So therefore, this is the smaller size that we have that's really available to you at all times. The 10 microliter to 100 microliter. Now, before I go further, I want to talk about this term microliter. Okay, so this term micro is this U that has a really long stem on it in the very front. So think of this as the Greek letter mu, okay? So microliter is not really used that often in the healthcare facility. And the reason is because nurses and physicians, they get into a hurry. With all good reason, they get into a hurry sometimes. So could you imagine trying to write this U with this long stem very quickly, and you're going to see how that maybe could turn into something that looks like an M. Now, do you want a nurse to give you milliliters of a drug when they should have been giving you microliters of a drug? No, of course not. So what you'll see in clinical side of the house very often is this MC, which means micro. Microliters or micrograms, G for the gram, of course. But that is typically the unit that you would see in that type of environment. For the chemistry side of the house, we are talking about the same volume. We're still talking about micros. We just use a different unit for that, and that unit is this U with a really long stem in the front. All right, so that's our shorthand representation of a microliter. All right, so a micropipetter will give us microliters as far as volume goes. Now let's talk about a relationship here. In general chemistry, if you've taken one of those general chemistry classes like Chem 151 or 152, you went through a moment in time where they were talking about conversions. Conversion units. How can you convert one unit over into the next? So typically what they do is they start you off with milliliter. All right, so milli, M-I-L-L-I, milli is in reference almost to like a millennium. And if I asked you, okay, how many years are in a millennia? Then you would hopefully come back and say, well, millennium, that means 1,000. Okay, well, that's good because that's what it means in the scientific community as well. So when we're working in a lab and we're working in milli units, we are working in 1,000. That's how I want you to kind of remember this and regard this. So for instance, milliliter. Well, there is 1,000 milliliters in a liter. And a liter is what we would call the whole unit. Okay? So sometimes liters are just way too big. And we go to milliliters instead. 5 milliliters, 10 milliliters, 15 milliliters, 25 milliliters, 50 milliliters. And if we have to compare these two and relate it from one unit to the next, 1,000 milliliters is equivalent to 1 liter of that stuff. Okay, well, this works for any unit, folks. So 1,000 milligrams is equal to 1 gram. So once again, take a gram of stuff. You can visually see that gram of stuff on a balance. And then take that gram and divide it up into 1,000 pieces. Each one of those little pieces will be called a milligram. That is the relationship here. And unit, no matter what kind of unit you put onto this thing, that's what it means. So 1,000 millis of anything is equal to that base unit. So for instance, 1,000 milliseconds Well, that is equivalent to 1 full second in time. Once again, a different unit, but it still has milli in front, and that milli is in reference to a number, and that number is 1,000. Well, we're working with micropipettes, not millipipettes. Okay? Millipipettes would be delivering volumes in full-blown milliliters, so quite large, and we do have those. We do have automated pipettes that will deliver 5 milliliters, 10 milliliters, 25 milliliters at a time in a more automated fashion. But that's not what you're going to be using today. What you're going to be using today is a micropipetter. So we need to talk about the term micro. Well, if you go back to the 80s, as a kid growing up, you often heard of this thing called micro machines, right? Little bitty, tiny little toy cars and stuff that we could play with. We could probably swallow them and choke on them, and our mom and dad wouldn't have even cared. But micro is this idea that something is super, super tiny. And micro is going to be in regards with a million. So 1,000,000 microliters is going to be a liter. Some people will often regard this as 10 to the 6th power. Why to the 6th? Because there's 6 zeros that are there. So 1,000,000 microliters is equal to a liter. And we can talk about micrograms. As you can imagine, super, super tiny things. And that is equivalent to a gram. We can talk about a microsecond. So very brief moment in time, of course. And that would be equivalent to 1,000,000 microseconds is a second. So once again, you need to think of this as if I take a gram of substance and I put it on a balance, and I take that substance and I divide this substance up into 1,000,000 pieces. That one little bitty millionth of a piece is the microgram unit that we are talking about. So we go even shorter. Folks, here's the story though. Even in our lab, we can go smaller than this. Even in our lab, we can measure things that are smaller than micrograms. Can you believe that? So 1/1,000,000th of a gram we can easily detect on some of our equipment. And we can go lower if needed, depending on the circumstance. So even though this seems like a really, really small amount of substance that we see, that we can work with, we can easily record and report these values, and that's the power of working in a laboratory and analyzing samples, whatever type of sample that might be. So the issue with the micropipettors, this is why I bring up that intro conversion, is this whole concept of going from milliliter to microliter. Okay, we've already talked about a milliliter. Well, there's 1,000 of them in a liter. And then we've talked about 1,000,000 microliters in a liter. But very often we have to make the conversion between mils to micros. Now, we can go through full-blown dimensional analysis and do this stuff on a sheet of paper and make it prim and make it proper and make it pretty, draw our lines, do the top unit on the bottom unit, and blah, 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 blah. But there's something a little bit easier that's going to be a little bit quicker for you to get used to. So, for instance, let's say that the lab tells you you need 3 milliliters of a solution. How many microliters of solution are you needing to use? And this is how we do it. Look at the 1,000 and look at the 1,000,000. What's the difference between these two numbers? It's 3 orders of magnitude. There's 3 extra zeros there. So milli is going to be a bigger unit than micro, right? If I take a gram of substance divided up into 1,000, that is a milligram. If I take a gram of substance and divide it to 1,000,000, that's a much tinier amount, maybe just a little speck. I can't hardly see it. But that's 1,000,000th of a gram. So the way that you need to keep this in mind, milli is a bigger unit, which means in order for microliter to catch up with that, folks, we need to add 3 zeros onto this number. So 3 milliliters would be 3,000 microliters. All right, so let me do you another example. Let's say that we need to pipette 0.5 mils. Well, how many microliters would that be? You move the decimal 3 times. You make this number bigger because microliter has to get bigger in order to catch up with it. That's how, again, I want you to think about this. So 0.5 milliliters. Well, there's my first move to the right, my second move to the right, and my third move to the right. That means I need to pipette 500 microliters in order to get a half of a milliliter. Okay? Let's do some more, just to get more comfortable with it. Let's pretend that the lab tells me to measure out 0.1 milliliters. Super tiny with a glass volumetric. I don't want to do that. I hope you don't want to do that either. So I move the decimal 3 times. So there's my first one, there's my second, there's my third, and this is 100 microliters that I need to be dialing in to the micropipette to use. If the lab procedure told me I need 0.5 mils, 0.5 mils, again, super tiny, I'm not going to use a volumetric pipette for this. It's too small. I'm going to use a micropipetter instead. So I'm going to move the decimal 3 times. So here is the first move, and then here is the second move, and then I need to move it again. There's my third. So 0.50 microliters. Well, we don't write zeros in front of numbers, so we'll get rid of that, and that means 0.05 mils is the equivalent to 50 microliters. If we can go this way, we can go the other way. That's not a problem. So let's say that the lab experiment says you need to measure out 725 microliters of solution. How many mils would that be? Well, I know that mil is a little bit bigger as far as size goes. So 725 microliters, I still move it 3 times. That's the order of magnitude that's different. So instead of moving it to the right, I'm going to move it to the left. 725 microliters is equivalent to 0.725 mils. Okay, 100 microliters would be equivalent to 0.1 milliliter. If I do 25 microliters, that would be equivalent. Okay, here's my 25, there's my decimal. I'm going to move it once to go between 2 and 5. I move it again, and that will be my second move. And I move it again, and that will be the third move. So 25 microliters would be the equivalent of 0.025 milliliters. All right, so that's the relationship here. Now, the micropipettors, again, they come in different versions. They come in different qualities. What we have are student versions because, folks, these things can get very, very expensive. And when I say very expensive, I'm talking about $500 for just one. So it's very important that you take care of these the proper way. It's very important that you do not abuse them. It's also very important that you understand how to operate them so that way you're not screwing these up for us. Could you imagine if we had a class of 14 people, we give each person a micropipetter, they don't know what they're doing with them, and they end up messing them up. This is 500, 500, 500, 500, 500. Before we know it, I'm going to go to the gas station to try my luck at winning the lottery in order to replace all of these micropipettors. So you have to be very, very careful with these because they are expensive. Here's a different view of a micropipetter that has multi-channels. over to the left-hand side. And then what you're going to see in image B right here is more of a digital single-channel micropipetter. So this allows me to dial in an appropriate number and allow this battery-operated system, for the most part, to suck up the proper amount of volume for me. So that way I don't have to worry about, am I using the micropipetter the proper way? Here's another listing of different micropipettors that are out there. Here, you're going to see they are broke down in different microliter sizes that they can deliver. So this one down here at the very bottom in red, this goes from 1 to 10 milliliters. So once more, we do have micropipettors that go very big, but we just don't have those in our lab. Okay. Here down below, we see that this micropipetter goes from 100 to 1,000 microliters. And this is the most common. That's why I've put a star beside of it. So 0.1 mil to 1 mil. That's basically what that represents. And then the other one with a star is up here toward the top. And this is a 10 to 100 microliter. And 10 to 100 microliter, that 10 basically means 0.01 mils. Again, super, super tiny, folks. And if I gave you a glass pipette and I said, measure me out 0.01 mil, you're going to look at me and you're going to go, you're crazy. I'm not going to do this. It's going to be very difficult, but we can. Here's a multi-channel pipette. Notice the price tag on that. Expensive. $12.20 per micropipetter. Again, tons of money wrapped up into the micropipette world. Automated pipettors. Well, automated pipettors are out there. They're not really classified as micropipettors, but automated pipettors are more of these kinds of concepts that these are battery operated. You can push a button, it sucks the sample up to where they need to go. Automated pipettors also fall into the category of larger volumes, like 3 mils and 5 mils and 10 mils, because we are not measuring microliters. So if we're not really measuring microliters, why do we want to call them micropipettors? I hope that makes sense. So instead, we would call those automated pipettors instead of micropipettors. So just kind of a formal lingo, I guess, building our vocabulary up in the world of wet laboratory technique. These micropipettors have to take tips, and here are different tips. The tips are not universal, which means that the tip does not fit every single micropipetter that we have in the lab. These tips are going to be universal as far as the size goes, but that's about it. So the 100 to 1,000 microliter micropipetter, that will have a tip that fits it. However, when you pick up our 10 to 100, that's a different size. And that different size micropipetter will have a different tip that comes along with them. So you want to make sure that you are using the correct, hint, hint, make sure that you're using the correct tip with the micropipetter that you have decided to use in the lab. The other thing that people typically do is that when they put these tips on, they start sucking up these solutions and stuff, right? I mean, that's just typically what we do. But they never look at the micropipetter tip. And that tip is going to be very important because you want to make sure that there's no air bubbles in that system. Air bubbles are going to be bad, just like they were in volumetric pipettes. Air bubbles will take up volume. That volume takes up space. And if you have air bubbles in the tip, you are not going to be delivering the proper amount of volume. And then you're going to bring us your data, and you're going to go, could you check my numbers? And then I'm going to look at it, and I'm going to say, nope, not good. Go back, redo it. And then you're going to look at me and say, well, it's just a micropipetter tip. How am I using it the wrong way? And there's a possibility that you will be sucking up air bubbles into the tip if you're not very careful. These tips will often come into micropipetter boxes like you see here. So in your lab drawers, you're going to have two sets of micropipette tips. There'll be a large tip for our larger micropipettors, and then there'll be a smaller tip, of course, for the smaller micropipettors. Each one of these typically will run $80 to $100, as you can see here in the listing. So here we see a typical micropipetter tip for that type of micropipettor, and it's going to say 10 to 1,000 microliter wide bore tip, single tray. So literally, I open the lid up, and there's going to be rows of micropipette tips ready to go here. And the only thing that I have to do is take my micropipetter and put it on top of the tip, squeeze down a little bit just to secure it, latch it onto the micropipetter, and then lift it straight up. That's all. So this will allow you to load a tip without actually touching the tip. And that's very important, especially in the microbiology and the biotechnology world. We don't want your nasties onto these tips that we begin to use. If you've never used a micropipetter before, here are some of the directions on how to use it. Up here at the top, depending on what you have, you're going to see a plunger. And this plunger, people typically put their thumb on it. And of course, this plunger moves up and down. Well, when I push the plunger down, there's going to be two stops. So the first one, this height here, is what we call the rest position. That rest position means that's where that plunger is going to stay. I'm going to push my thumb down on the plunger, and I'm going to get to the very first stop. Okay, this very first stop is kind of like me sucking some air into the system. I'm getting ready to squeeze the bulb, and by pushing down on that plunger, I have squeezed the bulb of a volumetric pipette now. That's the equivalent to that. So I've created some air. Then I'm going to put the tip down into solution. Notice what I said. You push the plunger down first, then you put the tip down into the solution. If you do not do this, what will happen is that you will turn into a 5-year-old, a 6-year-old, and you will put your micropipetter down into the solution, and you'll push the bulb down, and you'll see your solution go. I mean, that's what you'll see. Air bubbles will go everywhere. Your solution will splatter everywhere, because what you're doing is that you're forcing air down through the tip, and that air is now going into your solution, and it's bubbling, just like what a 5 and a 6-year-old would do if they had a straw, sticking it down into a Coke bottle and beginning to blow through the straw. Nobody wants that to happen, right? So plunger down first stop, put the tip down into the solution, and slowly let up the plunger. Did I make that clear? So slowly let the plunger up, because you want to make sure that you do not create a air pocket into the micropipetter. If you do, you have just incorporated bubbles. And we already talked about the problem with the bubbles. We don't want those to happen. All right? Then when you go to deliver, you will point this tip down here at the bottom into a container, and you will push down onto the plunger at the very top until you get to the first stop again. And that will deliver most of the solution out of the tip. But there still could be little remnants that's in there that needs to come out. So the micropipettors will have a second stop. And the purpose of the second stop is you push it down even further. Boop, there it goes. And that forces a little poof of air to come out of the tip and squeeze out any extra droplet that might be left behind. So the first stop is to suck the liquid up, and then you point it into the container that you want to deliver in. You push it back down to the first stop. That will get rid of most of it. And then there will be a second plunger stop that will then blow out any extra that does not need to stay in there. Another thing that people forget to do is check to make sure the tips are working the proper way. You do not want to see leaks here, folks. Leaks are going to be bad. So no leaks with the micropipettors. That is a very easy thing to take a look at. Typically, people will grab their solution, they'll pull their solution up into the micropipetter tip, and then they will hold it up and they'll look at it for just a brief moment. If they see that that tip is loose, then your liquid will start to come out of the tip, and you'll start to see a droplet that will form on the outside, and you do not want that to happen at all. So you do not want to deliver that volume, because that volume is going to be incorrect if you're not careful. Okay, so what could go wrong? When you're in the lab and you're working with these micropipettors, what could actually go wrong with your technique in order to provide a wrong or phony volume? Well, first is just simply operator error. You just don't know how to use it. And that's the purpose of today. We want to train you how to use it the proper way. So that's what this whole learning technique is going to be about. How do you use the micropipetter properly so that we can get rid of number one? Because when we turn you loose into a lab, we want you to be able to comfortably use a micropipetter. The next thing that could go wrong are just simply the properties of the liquid. The micropipettors are made for things like water, okay, something aqueous. They are not made for very viscous solutions. And I hope that if you've taken a previous science course, you know what viscous means. If not, then that's okay. I'm going to define it for you now. Look at me. All right, so viscous solution basically means super thick. So these are things like honey. Honey would be a very thick solution. A micropipetter, folks, is not going to do a very good job sucking honey up into that little tiny hole of the micropipetter. It's just not going to work. And there's other solutions that are out there that are very similar to honey. And I cannot use micropipettors in order for that to go on. Sorry, it's just not going to work. The other problem that I see are very volatile solutions. And again, definition, this should be covered in Chem 151 or 152. If not, I'll do it here. Volatile does not mean boom, explode. Sorry, that's not the definition of volatile. Volatile means that it evaporates very easily. So if you squirt it onto the lab bench, you'll turn your back toward it, and then you'll turn around and you'll look at it, and it might already be evaporated off. Volatile solutions do not behave very well in a micropipetter. They are going to leak out of the tips. The vapor is going to fill that chamber of the tip with vapor, and that forces the proper amount of solution from coming in. So volatile solutions we typically do not use. Viscous solutions we typically do not use for those purposes. Another thing that can affect it is the environment. So these are temperatures and pressures of the room. For us, this is not really a problem. As far as the pressure goes, we're at sea level pretty much, folks. So we don't have to worry about elevated altitudes or anything like that. As far as temperature goes, well, you know, unless the air conditioner breaks down in our lab, we are typically always at room temperature, anywhere between 20 to 25 degrees. So as long as we are working in those conditions, then we are fine. You can't blame it on the environment. But depending on the lab and what they do with it, this could be a problem for them. It's just not a problem for us most of the time. And next is the condition of the pipetter. And this really boils down to the maintenance and the care. So you can't just buy a micropipetter and it lasts forever and you not do anything with it, okay? Over time, these are going to get used. There are gears and mechanics that are on the inside of these micropipettors for them to work. And those gears and those mechanical pieces and the gaskets are going to start wearing out. And over time, these micropipettors do get pretty crappy. So if they do, we try to maintain them. We try to calibrate them, and that's the purpose of the calibration. We want to ensure that they are delivering the proper amount of volume. If we try to calibrate them and they still do not behave the proper way, then this is either number one, replace the internals of the micropipetter, or number two, which is a little bit easier sometimes, and maybe even cheaper, you just buy a whole nother micropipetter. That's the easy way to fix that problem. In a laboratory, depending on who you work for and what type of environment you work in, you might see a dedicated micropipette and that dedicated micropipetter will be used for the same thing every single time. So don't be surprised if you see this in a lab. Some people like to do that. That way they can keep track of that micropipetter and what that micropipetter was used for. So for quality purposes, it might streamline their process a little bit better. So don't question why maybe lab managers or different types of companies will do this. They're doing it because in the long run, it's really easier for you to keep track of things. Also, depending on the environment, you might see dedicated micropipettors assigned to certain people. So this will be your micropipetter that you will use when you go into work, and it will be up to you to make sure that that micropipetter will be performing the proper way. Again, that really depends on the company. That really depends on who's in charge and what they decide to do. Couple of things. Number one, do not drop a micropipetter. You'll mess the gears up. There's a possibility that you'll break them, and these are $500. That's a paycheck. That's your first paycheck. When you graduate from the program and you get your first paycheck, I'm coming for you because that $500 is going to be mine. Next, rotate the adjuster for volume above or below the range printed on the front. Okay, well, what does that mean? Well, there's a display in the front, and this display will have a number on it. Okay, so let's say the micropipetter that I get is 100 to 1,000 microliters. Okay, so I take this microliter and my directions say pipette 50 microliters. So I take this knob that's on the adjuster of the micropipetter, and I turn, and I get down to 100, but I need to go down to 50. So I'm going to keep turning and turning and turning, and there's going to be some resistance on it, and I'm trying to take it to 50 because I don't need 100, but what I'm going to do, I'm going to break it. And the reason is because this micropipetter cannot go that low. Sorry. This micropipetter can only go to 100. I can't dial it any lower than that. And the micropipetter will only go to 1,000. I cannot take it any higher than that. So that is a problem. So if you feel resistance on the knob that you are turning to adjust the volumes, that's the big thing here. You are probably using it the wrong way, and you're doing something you're not supposed to do, and that could completely damage and ruin the micropipetter. Next, never place this into a flame, for goodness sakes. I mean, I know that I have to say this kind of stuff, but I hope that you have enough common sense that you're not going to take a micropipetter and put it into a flame. But who knows? I mean, maybe one day, one semester, somebody's going to say, I wonder what happens if I put this into the flame. What's going to happen to this plastic micropipetter? Okay, whatever. Use without a micropipetter tip. Okay, again, I don't think that I have to say this kind of stuff, but folks, I just can't take things for granted. So when you use the micropipettors in the lab, you always want to make sure there's a tip on the end of it. You never want to just take the micropipetter without a tip and stick it into a solution and suck the solution up into the mechanics of the micropipetter. That's silly. It's not going to work. Next, never lay the micropipetter on its side. The reason here is because these solutions that are in the tips, if you lay them on the side, they can go up into the micropipetter and they can damage the micropipetter. It's also shown that micropipettors that stay vertical, up and down, the way that they are meant to be used, last longer than the micropipettors that lay flat onto a countertop, which is why we always have risers and micropipette holders. We never just want to be nasty about it and just throw the micropipettors all over in the lab and just leave them laying. So we always want them in the vertical position when we can keep them that way. Next, never place the bottom of the micropipetter in a liquid. That kind of goes back up to never use it without a micropipetter tip, because that liquid can go up into the micropipetter, and those gears and those gaskets and those rubber seals and everything else can begin to ruin. Finally, never allow the plunger to snap up really quickly. We talked about the whole slow release of the plunger. and that is in there for a reason, and that is in there to prevent air from going up into the tip. And it's also mentioned because that also prevents liquids from going up into the micropipetter. As you can imagine, very quick suctions could suck the solution up too fast, and now all of a sudden that solution's going to go up into the tip, and then it's going to go up into the micropipetter, and now you have a ruined micropipetter. If you are curious about the mechanics of the micropipetter, here's an image of a micropipetter that has been taken apart. So a couple of things here. The plunger buttons are typically always up here at the very top. As you can imagine, that's what's going to suck up your liquids and dispense your liquids. This little turny valve that I told you that this is what you adjust for your volume, those are actually called micrometers. So you're going to turn the micrometer until you get to the volume that you actually need to dispense. You're also going to have some type of display. Sometimes these are digital, sometimes they're analog. It just really depends on how much money people have paid into the micropipetter. So this in the very front is going to be the area that you can kind of just quickly look at to see what the micropipetter is dialed in at. Down here is the piston assembly. So as you can imagine, this suction device here that connects to the micropipetter dial up here, that has to have a connector. And in this little connector, that's where you're going to start to see some springs and some valves and everything else in between. Down here at the top or the bottom, this is what we call the shaft. The shaft again will be used to go onto a micropipette tip, and that tip will be attached to the shaft. So that way when this solution gets sucked up, it will only go into the tip and not the micropipetter. And then over to the side, you'll often see a tip ejector. So once you're finished with it, how do you get the tip off? Well, sometimes I don't want to touch those, right? Now, who knows what could be inside of that micropipetter tip. So there's going to be a button up here at the very top, and it says tip ejector button. And I'll just push that down with my thumb, and that takes this metal piece on the side of a micropipetter, and it pushes that tip off of the micropipetter. Over here to the right-hand side, you're going to see maybe a more detailed look at this whole piston assembly. So here, of course, you'll see something that looks almost like a needle here with a spring on it. And then you'll see some gaskets, some O-rings, some seals down here at the very bottom. So if you have to calibrate them, folks, you'll have to take this off sometimes to clean it and then put it back on. However, this is something that we rarely have to do in our lab because you will know how to use these the proper way. And that's good for you. And that's good for us because that means you listen. And that means that these videos are worth it, right? At least that's what I'm going to tell myself so I don't feel depressed when I record hours of videos at a time. All right, so here's the last slide that I need to show you of micropipettors. And what this is basically a calibration form. So sometimes you might not do anything with a micropipetter at all other than dispense water with them. And the reason that a company would tell you to do this is because they want to make sure that these micropipettors are delivering the volume that they're supposed to be delivering. And that's what this form is representing. So up here at the top, you're going to see a calibration technician. They want your initials here and the calibration date. And then when should someone calibrate it again? The micropipetter has a number identifier on it in a real working lab, so that way we know exactly which micropipetter has been calibrated and which has not. And then they're going to give me the location of that micropipetter. They're going to tell me a temperature at which these solutions were at and how these numbers were formed, because temperature does play an effect on volumes and mass amounts, so that's going to be a pretty important number for me. And then down at the bottom, you're going to see nominal volumes. So it looks like this procedure is telling this person to pipette this amount 6 different times. 500, 500, 500, 500, 500, 500. And they're going to dispense that amount onto a mass or a balance to get a mass. And I'm going to get the initial weight of the tube and then the weight after that water was dispensed. So they're recording those masses down, and this is something very similar to what you'll be doing in the lab today. And then in this last column, you're going to see the weight of the dispensed water. And that's just simply a subtraction. Once more, very similar to what you'll do in the lab this afternoon when you go in, or whenever you go in. So here are the volumes, and what they decide to do at this point is change these grams over to microliters using the density of water. And then they take an average down here at the bottom. And then they look at the inaccuracy, or what we would call error. And that error is then compared to an acceptable limit. Is the error too much, or is the error okay? We know there's going to be error with it. We know it's going to be off. How much is it off? That's what we're curious on. So this is a typical calibration for a micropipetter. And if this thing fails, then this micropipetter gets removed from the lab, and we begin to calibrate it, we begin to clean it, we begin to see if we can fix it, and then if we cannot fix it, we'll trash it, and we'll purchase another one. So this just gives you an idea of what you're doing today actually has a purpose. What you're doing in this lab procedure is actually done in real life. And it's a very important technique because these things have to be calibrated, because if they're not calibrated, people cannot use them in a real working laboratory. And these calibration checks, they have to be documented, they have to be saved, they have to be filed, and they have to happen every so often. It's very, very important for this to go through. Okay, so that's really all that I want to say about this lab experiment and using a micropipetter. So take a look at the lab procedure. You're going to see something very similar to this at the very end of the data sheet to that lab document. We're wanting you to measure out certain amounts. We want you to take those certain amounts, give a mass, and then we want you to report those masses to us, so that way we know if you are using the micropipetter the proper way. All right, so if you've got questions, you know how to get a hold of us. Email, text if you've got numbers, and we'll be here. And we'll be waiting. Just like you waited just now to see what else I was going to say. All right, so good luck in the micropipettors. I don't think that you'll need it. I think once you get the hang of it, the first 1 or 2 dispenses, this lab will blaze right through. I think that you'll be perfectly fine. So good luck.